Okay, we're going to start our unit on modern physics, starting with relativity. And something you need to keep in mind is that we're going to stay to the very, very basics. You're not going to have a full understanding of anything in the next couple of weeks. Um, it's very, very in depth, it's very, very advanced. But we're going to get some basics down, things that we can hold on to, things that we can define, theories that we can describe, and we're going to go from there just so that we can understand what it is. So modern physics started in the 60s or so, really advanced in the 60s. So anything before that's pretty much considered classic physics, and then we get into our modern physics in today's age. What we know as the classic physics, or what we've been studying all year, is Newtonian physics. Okay, that's all the stuff that we know. Um, this little chart here, let's put velocity over here and size down here on this axis. So velocity is going to be anything from 0 all the way up here to the speed of light. All right, let me see if I can zoom out so you can see the whole chart at once. There we go. Um, So Newtonian physics is going to be things that are happening at a relatively slow speed, but that's still everything up to uh, the speed of sound, things like that. So it's not that it's super slow; it's just not near the speed of light. Once we get near the speed of light, Newtonian physics starts to get a little bit awkward. Okay, um, but we fix that with relativity, or we fix that. Einstein fixed that with relativity. So when we start getting near the speed of light and what we call relativistic speeds, relativity starts taking over, and then we can handle the physics at that speed. Now, if we look at size, the scale actually goes backwards. We start with large items, and we go to the smaller items. So large items are going to be anything large like planets, galaxies. Yes, that works. We've done calculations with that, right? When we did circular motion, we calculated orbital periods and things like that. But large as well is down to even some atom size things. Small, when we say small, what we really mean is subatomic. So here we're talking about protons, neutrons, electrons, and all the other subatomic particles that we need to introduce. So we're talking about very, very small. And when we talk about very, very small, Newtonian physics once again gets a little bit wonky. And we have to look into a field called quantum mechanics. So we're going to be looking at relativity this week, or for the next week or so. Then the week after that, we're going to be looking at quantum mechanics. We're not going to really touch this area too much. When you're going the speed of light and you're really small, you get into what is known as the quantum field theory. And this is very theoretical physics. Um, and we're just not going to go that far this year. So we're going to spend some time in relativity. We're going to spend some time in quantum mechanics. Then we're going to kind of wrap up the year. So let's start with something very, very basic today. Galilean relativity. Galilean relativity is what we already understand. We know this backwards and forwards from what we've been learning all year. Of course, the guy that came up with Galilean relativity was Galileo Galilei. Galileo. So make sure you have that name down. So Galileo developed Galilean relativity, which he, of course, just called relativity at the time. And that relativity says the laws of mechanics, so in other words physics, have the same mathematical form in every reference frame that does not accelerate. So what does that mean? Well, the laws of mechanics that have the same mathematical form, that's saying that physics works. All of our formulas, all of our theories, all of that stuff works as long as we are in what is called a reference frame that does not accelerate. We give this another name. We call this an inertial reference frame. Just to say it a little bit faster. But a frame that does not accelerate does not mean that it's standing still. Acceleration is the change in velocity, so we're just looking for a zero change in velocity. So it could be something that is sitting still and not moving at all, or it could be something that's moving at a constant speed. Okay, we see this all the time. If we're just standing outside, we look around, physics all works like we would expect it to. If we're in a car, we're driving down the highway, physics would, you can toss a ball up in the air and it's going to come right back down into your hand. It all works the way you would expect it to. If you're looking from one frame of reference to another where one is moving and the other is not, then physics doesn't work exactly like we would expect it to. If we're looking at somebody throwing a ball up in the air in a car, if we're outside of that, we would expect the ball to go up and then down in the same spot without moving. Well, we got to take into effect the relative speed of that car, and the ball's going to go up and down. So in the car, the ball goes up, down, in place. Out of the car, we would expect it to go up and down, but the car's moving. So it actually does this. So when we take into consideration the velocity of the car or the relative velocity of the car, then physics works again. So we've actually thought about this, and that's why we talk about systems and things like that, where we isolate a lot of our problem into one specific area. So we know how this works. So Galilean relativity we're comfortable with. Physics works as long as we're in a non-accelerating reference frame, which we call an inertial reference frame. The problem that we run into is when we approach the speed of light, which again, the speed of light is 3.00 times 10 to the 8th meters per second, extremely fast. When we start approaching things at that speed, which we call relativistic speed, physics didn't quite work the same anymore. And so we're going to look at more of that next time. I just wanted to get the basics down today, that you understand when we're talking about relativity, that's near the speed of light. When we're talking about quantum mechanics, that's when things are subatomic. Newtonian physics is what we've been studying all along. And quantum field theory is just way, way advanced and theoretical, where we're doing both of those things, fast and small. We have the first of our three relativity ideas here, the one that we've been working with and the one that we understand almost intuitively, is the Galilean relativity. Physics works in inertial reference frames. And then the first major problem with that is the speed of light. And we're going to see how Einstein handled that